Hello and welcome everyone to this acoustic webinar about adaptive acoustic radiation with Actran. Here is the agenda for this presentation. I will first give an introduction to acoustic radiation problems. Then I will recall how acoustic radiation calculations are performed in Actran. So what is the computational process? What are the key ingredients of the Actran model? Then I will actually talk about adaptivity. What is adaptivity and how you can use adaptivity in Actran 15 through adaptive PML components, exterior acoustic components, and RADACT. I will then demonstrate you in Actran preprocessor, Actran VI, how to set up an adaptive acoustic radiation analysis in Actran. And finally, you will be able to ask me any question you like regarding the content of the webinar during the Q&A session. So let's start with the introduction, and let's start with the first question. Why do we need noise to be studied? There are three main reasons why companies are studying noise and acoustics. First, the manufactured products need to accommodate for more and more stringent standards in order to be sold. The standards are becoming so restrictive that it actually becomes, in more and more cases, a dimensioning factor. The second reason is that company wants to build products with good acoustic performances to improve comfort. For example, the noise perceived by the driver of a car or the driver of a truck certainly is a marketing argument nowadays. And finally, in some cases, noise can cause damages. For example, when a structure is placed inside a launcher in order to be sent to space, it must not be damaged by the very intense noise generated during liftoff. This aspect will actually be presented during the next webinar we will be holding. So if you are interested in simulating noise in the context of a space application, do not hesitate to register to this webinar. So you can see with these 3 points that noise needs to be studied in many circumstances. How can acoustic simulation help studying and facing these noise issues? In order to assess the acoustic performance of a product, tests are usually performed. The problem is that building a prototype is usually costly and occurs late in the development cycle. If we take the example of this ship engine here, you can anticipate that only few prototypes can be built and tested. With acoustic simulation, it is actually possible to perform more iteration, as it is less costly and less time-consuming than building a prototype and performing the tests. And the acoustic simulations can be performed early in the design process, allowing a better understanding of the physical phenomena occurring in the system. And based on this knowledge, it is then possible to adapt and to do more intelligent iterations. So as NVH engineers nowadays, the two main challenges that you need to face are the following. The first one is that you need to study the noise source mechanisms in order to assess structural design changes from an acoustic point of view. So what happens if I modify my material properties or my structure shape? What is the impact of this modification on my acoustic performance? The second challenge is to study the noise propagation mechanism. So the objective of that is usually to decrease the noise transmitted to the environment, and to this end, the acoustic performance of covers or noise redirection panels or insulation materials needs to be assessed. And in order to include acoustic simulation in the development process, it is really important that the acoustic simulation software fulfills 4 conditions that I will present you now. The first one is that it must be easy to use. So it is easy and fast to create a model. It must be performant, because you want to have results in a fast way. It must be accurate in order for the provided result to actually be meaningful and relevant. And finally, the software must be able to output data of interest that can be used by an engineer to improve the design. So these outputs can be rather simple outputs, like the sound pressure level at microphone position, but can also be more advanced ones, like the contribution of some parts of the structural vibration to the generated noise, or the efficiency of an acoustic treatment. During this presentation, I will focus on the ease of use and performance aspect, and we will present the other aspects during other webinars. So let's see how acoustic radiation is performed in Actran. This is just a recall on how it is done. So just to give you the basics and give you the keys to understand what I will do in the next part. So acoustic radiation problems are vibroacoustic problems. So we have the vibration of a structure that induces a pressure fluctuation. And this pressure fluctuation will also induce vibration in the structure. When we consider both effects, we are talking about a two-way coupling or a strong coupling. Of course, this fully coupled problem can be solved in Actran, but in many circumstances, we can neglect the action of the pressure fluctuation on the structure vibration, and in this case, we are now talking about a one-way coupling or a weak coupling. This assumption that the pressure fluctuation do not have any impact on the structure vibration is very much valid when we consider that the vibration of a rigid and heavy structure in a light and open acoustic media like the air. However, for acoustic radiation in heavy fluids like in water, or for acoustic radiation in closed cavities, the strong coupling must be taken into account. The advantage of this one-way coupling is obviously the strong gain in computational time that can be achieved. The structural and acoustic problem can be solved separately, so you can input the structural result that you have from any structural model you have already run, and only run the acoustic calculation. And this acoustic calculation only contains acoustic degrees of freedom, so it actually requires less time and less memory to run. So let's have a look at what is the simulation process for studying a radiation noise in Actran. First, you need some vibration levels that are computed by a structural code. You input this vibration to the Actran radiation calculation, and this calculation will give you results that you can post-process in order to improve your design. So this acoustic radiation requires an input, the vibration of the structure, and also a second item, which is the acoustic mesh. This acoustic mesh usually is made of three different elements. First, we have an acoustic coupling surface. So we have a surface, a closed surface that is going around the structure. We then have some finite elements to support the acoustic fluid component, so what we call the near field. And then we have a surface that we call the non-reflective boundary condition surface. And why do we have this surface? We have this non-reflective boundary condition in order to fulfill two objectives. First, we need to ensure that there is no wave reflection when the pressure waves are passing through this surface. And then we also want to have accurate acoustic results beyond the finite element domain. So if I place a virtual microphone outside of this finite element domain, I can have acoustic results there. So how do this non-reflective boundary condition can be done in Actran? We have actually two technologies available. The first one is the infinite elements. Infinite elements are the extension of finite elements to far-field radiation. So based on the nodes that are on this non-reflective boundary condition surface, high-order shape functions in the radial direction are used to ensure that there is no reflection and to compute the acoustic pressure far from the source. The second technology that is available in Actran is the perfectly matched layer technology, or PML. This method is an alternative or a complement to infinite elements for the radiation in free field. So in this case, we still have our vibrating structure here in green. We have our coupling surface around it and our acoustic components, so some finite elements in the near field. And what we will do is to add an extra layer of finite elements to progressively damp the acoustic wave. And then, if we want to have results in the far field, we are using Fox-William-Hawkins integral that is directly integrated inside Actran. So let me summarize how to do acoustic radiation in Actran. It's a two-step procedure. First, we have an excitation. This excitation is computed by structural code. So from this calculation, we have actually the structure mesh and some results fields. And we input this information to the BC mesh feature in Actran. BC mesh feature, which stands for boundary condition mesh, is the feature that allows to perform weakly coupled acoustic radiation. So you will input to this BC mesh the structure mesh, the result field, and also the acoustic mesh. And based on this information, the acoustic radiation can be computed. What you will see later during my demonstration is that in Actran 15, users do not have to provide the near field mesh, as it can be automatically created by Actran. So now that we've seen how we are usually doing acoustic radiation calculation in Actran, I will talk to you more about adaptivity and how we can use adaptivity to improve these acoustic radiation calculations. But let's start with the first question. What is adaptivity? Traditionally, when we want to do acoustic radiation calculations, we are using one mesh. This one mesh is designed for the highest frequency we want to solve. It means the smallest wavelength, so the smallest element size. And this mesh is used for all the frequencies we want to solve. So the computation time is actually the same for all the frequencies of the calculation. When doing adaptive acoustic radiation calculations, we will take our complete frequency range and divide it into smaller frequency bands. For each of the frequency bands, we will create one mesh that is adapted to this particular frequency band, and then we have a reduction in computation time for low frequencies. So this is what adaptivity is about, creating several meshes to perform the calculation in a wide range of frequency. So what are the key ingredients for adaptivity? Well, first, you need to divide your frequency range into smaller frequency bands. This can be done manually, so you can manually define some frequency bands in your adaptive component. And it can be done automatically using a particular keyword named adaptive factor. For example, in this case, we're interested in computing the response of the system from 100 Hz to 3200 Hz. And with this adaptive factor equal to 2, we'll have 5 different frequency bands, and we'll have one mesh for each of these frequency bands. So actually, the second key ingredient is the fact that the mesh creation should be automatic. You do not want to provide yourself Actran with these 5 different meshes. So this is possible in Actran 15 thanks to the integration of meshing tools directly inside the solver. And for each calculation that contains a component which uses adaptivity, a distance execution sequence must be run prior to the actual run in order to create the mesh. Once the mesh is created, the calculation runs as usual. So now that you know a little bit more about adaptivity, let's see how you can use adaptivity in your Actran calculation. The first component that uses adaptivity is the Adaptive Perfectly Matched Layer, or APML. So I presented you the PML technology just before. Actually, for this PML layer, to be effective, we need it to be as thick, thick enough to absorb the longest acoustic wavelength, and it must be meshed with elements that are small enough to capture the shortest wavelength. It means that if we are using one PML mesh for the complete frequency range, this PML mesh would be very large, very thick, and mesh with very small elements. This is obviously not what we want, because this would lead to very high computational time and resources. So APML actually, again, splits the total frequency range into smaller frequency bands and will create one PML mesh per frequency band. So at low frequency, we'll have a very large PML layer meshed with also very large elements. And at higher frequencies, we'll have a much smaller PML layer and meshed with very small elements. The second component that is using adaptivity in Actran 15 is the exterior acoustic component. So how does it work? You input this exterior acoustic component with the acoustic coupling surface. You also provide the thickness of the acoustic domain you want to create and the kind of non-reflecting boundary condition you want to use, so either infinite elements or PML. And based on this information, the exterior acoustic component during the distance execution sequence will create acoustic mesh in an adaptive way and in a totally automatic way. So it's actually a big benefit for a user, because you only have to provide Actran with the acoustic coupling surface, and the near field mesh will automatically be created, and all required components to run the calculation will also be created by the exterior acoustic component. So let's take an example. We have this coupling surface here, which is going around my structure. And in a first definition of the exterior acoustic component, I will specify a particular thickness, and I will say that I want a non-reflective boundary condition, which is infinite elements. When I run the distance execution sequence, meshes will be created according to these specifications. So in this case, I will have some finite element mesh in the near field, and then the surface supporting the infinite elements. And then from that, the calculation can be run as usual. If I'm using PML boundary method, the same procedure is applied. So I will input the exterior acoustic component with the coupling surface, the thickness of the acoustic component, and the PML method. And during the distance execution sequence, the mesh will be created. So we will have the mesh supporting the acoustic components, and then our PML layer. And again, you can then run the calculation in order to get your result. So with the exterior acoustic component, we wanted to make sure that users could do all kind of calculations using this particular component. So we actually made sure that it was compatible with as many things as possible in the Actran component and boundary condition library. The first thing I want to talk to you about are the baffle planes. So sometimes you want to introduce some perfectly reflecting planes in your calculation. This is sometimes tricky to mesh, but actually with exterior acoustic components, you just have to specify the coordinates of this baffle plane in the component definition, and the mesh will be created accordingly. You will see an example of that during the demonstration. Also, if you place some acoustic sources in the far field, like monopole or plane waves, they are localized by the exterior acoustic components and used in the calculation. And finally, if you are applying a diffuse sound field boundary condition on the same surface you are applying the exterior acoustic components, you will be able to excite your structure with this diffuse sound field, taking into account the masking effect of the structure. So, as I told you previously, the main advantage of using adaptivity is the performance. To demonstrate to that, I did a computation time benchmark on this gear case acoustic radiation model. So we want to compute the acoustic radiation of this model from 20 Hz to 4000 Hz. You can see that the mesh is created in an adaptive way, and then we can compare the timings with a calculation that is run the traditional way. So if the calculation is run the traditional way, we build only one mesh that is designed for the highest frequency. One frequency will take a certain amount of time to be solved, which is this amount of time here, and then it will take the same amount of time to solve all the frequencies of the frequency range. Whereas when using exterior acoustic components with the adaptivity, you can see that each time the mesh is changed, the computation time reduces. Actually, in this particular case, I was able to run the model with exterior acoustic components 3 times faster than the traditional model. So it's a very big gain in performance. Before going through the demonstration, I just wanted to have some words about RADACT. So RADACT is a module of Actran that is used to perform acoustic radiation analysis in batch mode based on an Actran formatted structure mesh, structure results, and acoustic mesh. So from these input here, RADACT is able to generate the Actran input file, compute the acoustic radiation analysis, and then post-process results to provide acoustic indicators such as frequency response functions, maps, or waterfall diagrams. In Actran 15, we integrated meshing tools and exterior acoustic components inside RADACT, so it is no longer needed to provide the acoustic mesh, and instead RADACT will use the mesh of the structure model to create the acoustic mesh, and then it will create the input file, run the calculation, and post-process the results. So this is how adaptivity can be used in Actran 15. So let's jump into the demonstration now. For this presentation, I have chosen to present you the model setup for a wind turbine gearbox acoustic radiation analysis. So I have the structural vibration of my gearbox that have been already computed, and I want to compute the acoustic radiation of this model. Before going into Actran VI, here are the specifications I have for this model. So I performed my structural calculation in Actran. I have a mesh file, which is mesh.bdf. I have a results file, which is results.p2. I want to compute the noise radiated from 10 Hz to 800 Hz with a 2 Hz frequency step. And I want to have a radiation of this gearbox in semi-free field. It means that I have a perfectly reflecting plane that is located just below my gearbox. So let's go to Actran VI now. I've already loaded my structure mesh here. So you can see it contains some 3D elements everywhere, and it also contains some openings. The first step is to create the acoustic coupling surface. So we want to create a surface that is closed and that goes around the entire structure. So the first thing I will want to do is to fill the holes. So I can go to meshing tools here in Actran VI and then select the fill holes function. The fill holes function requires me to input the maximum hole diameter I want to fill. So I'll actually measure what is the maximum hole diameter I want to fill here in this model by taking 2 nodes on this particular opening here. Okay, I go to measure, and I can see that the diameter of this opening is around 0.67. So I can go back to my fill holes meshing tools, put something like 0.7 in order to be slightly higher than this value to be sure I can close everything. I select my mesh in input here, and I can preview what the fill hole function will give. So in this case, I can see that the fill hole function will create the blue mesh, and it fills all the opening and even some parts here that are not really holes, but some recesses in the structure that the fill hole detected. It's not a problem. I will create this mesh here, and then what I will do is that I will remove these two parts that I don't want. So here and here. So my holes are filled now. I can create a closed surface around this structure. To do that, I'm using the shrink wrap function. This shrink wrap function inputs two parameters. The distance, I will put a distance of 0 as I want my surface to be as close as possible to my structure. And the shrink element size, which will be approximately the size of the structure mesh elements here. So I can select everything, create my shrink wrap in a new topology. So it will take some few seconds to run. And you can see actually that now I have a surface that is closed and that goes around my structure. As you can see, the shrink wrap function created some mesh which quality is not ideal. So what I will do is to remesh it using the mesh on mesh function here. Okay, so now I have my acoustic coupling surface. I have all I need as an input in the mesh point of view for my acoustic radiation calculation. I will create a direct frequency response analysis. I want to solve this problem from 10 Hz to 800 Hz with a 2 Hz time step. And I will actually create 3 items. The first item I want to create is the coupling surface. Yeah. This coupling surface will be used by the BC mesh boundary condition. So actually I need to create a domain first corresponding to my coupling surface. So I assign this coupling surface domain to my coupling surface component. Okay. I can then create my boundary condition, BC mesh. So I'm using Actran BDF mesh with Actran OP2 results. And I did my Actran calculation outputting displacement results. I'm selecting my coupling surface here, and that's it for the BC mesh. So the last item I have to create is the exterior acoustic component, which will directly, automatically create the mesh, the exterior acoustic mesh during the distance execution sequence. So I'm creating this component here. As I told you during the presentation, I need some items in inputs. I need my coupling surface mesh here. I need the kind of boundary condition I'm using. So in this case, I will show you with the APML boundary method. And I need the thickness of the acoustic domain I want to create. Usually we are taking something like 1/3 of the characteristic length of the structure. In this case, it corresponds to 0.5. The only thing that remains is to create a fluid material. So I will have air around my structure with default properties here. And as I told you during the introduction to this demonstration, I want to create a symmetry plane, a baffle plane, below my structure. Actually, I know the coordinate of this baffle plane, which is -1.2 in the y axis. And so I add this symmetry plane option in the exterior acoustic component definition. And that's it. My calculation is ready to run. The only thing that I'm missing right now are some post-processing, like some virtual microphone that I place in the far field, or some maps that I would like to output. I will not do that here because, well, it would take some more minutes and I don't have these minutes. So actually, let's open directly the final analysis that I completed already. And you can see that I just added some field points and field maps around the structure. So once I have my input file, you can see here my EDAT input file, I can run the distance execution sequence, and this distance execution sequence will create a folder Exterior Acoustic db.nav, which contains all the meshes that were created during this execution sequence. In this case, I have 25 meshes for my complete frequency range. You can load them in Actran VI to have a look at them. So I did that for 2 meshes. The first one is the highest frequency, so the mesh used for the highest frequency source. So here it is. You can see that we have the mesh supporting the acoustic components that I colored in blue, and then the PML layer, which is here in red. Everything is meshed with quite small element size, as this mesh is designed to solve high frequencies. If I load a mesh that is used for lower frequency, so for example around 100 Hz, you can see that the PML layer thickness will be far larger, but also meshed with far smaller elements, and the acoustic domain is also meshed with smaller elements. And then once I did this distance execution sequence, I have my meshes and I can run my calculation and obtain results, such as here I have the power that is radiated in the far fields. You can see what is the power radiated to the far fields with respect to the frequency. You can also look at the sound pressure level at a particular location of interest. Or you can plot the directivity of the noise around your structure. If I go back to Actran VI, I can also plot some field mesh here and see that at one particular frequency of interest, I have this particular pattern for the pressure field. So, okay, let me go back to the presentation. Let me summarize what I did during this demonstration. I wanted to create the model to study acoustic radiation of this wind turbine gearbox. I only had to create 3 items in the Actran analysis: the coupling surface, the exterior acoustic components, and the BC mesh boundary condition. I first ran a distance execution sequence in order to create all the meshes. In this case, the 25 meshes are created in 5 minutes, so it's pretty short. And then I was able to run the calculation. Again, in order to show you what the performances can be, I run the calculation using only one mesh or using several meshes. When I use one mesh, you can see that this calculation takes 9 hours to complete. And with this exterior acoustic components using adaptive mesh, I was able to run this calculation in only 3 hours. So only considering the computation time, I reduced by a factor of 3. Plus, I only had to provide the Actran model with the acoustic coupling surface and not the near-field mesh. So let's have some conclusions between the Q&A session. First, you have seen with this demonstration that it's actually very easy to define an adaptive acoustic radiation model in Actran. It only requires few inputs. Then in terms of computation performance, the mesh adaptivity allows drastic improvements in computation time for acoustic radiation problems. And overall, what is really important for us is that you are able to save engineering time, because first you do not have to provide the complete acoustic mesh, and then you do not have to wait too much to get your results of the calculation.